everyone, I hope you're doing well. In this video we are going to find planar density for simple cubic planes. Okay, so the planes that we are going to consider are 100. So let's quickly get started. First of all, we should know the formula that we are going to use for the planar density calculation, and we know that the planar density is given by planar density is given by following formula. It will denote planar density by sigma sign. Okay, that is equals to that. The thing I was gonna write here was correct, but there is no enough space to accommodate all of the words. That's why I'm using here the symbol for the planar density, which is sigma here, and that is equals to net number of atoms lying on the plane for which you are gonna calculate the planar density, the plane under consideration, divided by the area of the plane. And let me write here in the subscript of planar density as H, K and L. Now let's do it for the 100 case. Okay, for 100 plane in simple cubic structure, we are gonna find out the planar density right now. Here we are gonna find out the planar density of this plane in a simple cubic. Sometimes SC symbol is also used to show simple cubic. Okay, just like FCC shows face centered cubic, BCC shows body centered cubic. Similarly, SC symbol capital shows simple cubic as well. First step is to draw the plane inside the structure or unit cell you are considering. So we are gonna draw the 100 plane inside a simple cubic unit cell first, and that drawing actually guide us towards the solution. Okay, that drawing is crucial and you should know how to draw it properly. Okay, so take it seriously, because if you are considering the crystal theory, you should know how to draw different structures and all these things, and I'll guide you people throughout the process. And you should know how to draw planes from given Miller indices. Okay, I have uploaded a video where we have drawn several planes with different Miller indices cases, negative, positive, all positive, all kind of cases were drawn, and that video is really good. I highly recommend you people to watch that. So let's quickly get started with it. First of all, let's draw the cube. We'll make a block here. Okay, all these sides are equal to each other. Then another block right at the center or something, away from the first block. Then what we do is we'll join these corners, the similar corners together. The corresponding corner to this is this one, that is why I joined them together, this and this. Okay, equivalent corners, we joined them, and we can see that all of the indices here are positive. So the origin that we are gonna select is this point. Okay, this point is taken as origin whenever all of the indices of the plane are positive. If any of them is negative, if any of the index is negative, then you have to shift the origin. Okay, so these are some crucial steps, but here we can see the planes we are considering, all of them have positive Miller indices. So we'll be taking this point as origin throughout the problem. Okay, since it's the first plane that I'm drawing, that is why I'm demonstrating you people the detailed method. After that we'll do it quickly, so bear with me, have some patience please. I just want to ensure that you are getting everything in a single video. And we have 100 plane here. This is the index for x direction, this is index for y direction, this is index for z direction. We want intercepts from them, and for that purpose what we do is to take inverse of each of these index. Okay, these inverses gives us the intercept for the plane. okay, and we can easily draw the plane from those intercepts. So this is something that we are doing in a rough work. We have 1 0 0 indices, taking inverse to get the intercepts, inverse of each of these. So inverse of 1 is 1, inverse of 0 is infinity, inverse of 0 is again infinity. So this is the x-intercept, this is y-intercept, and this is the z-intercept. Okay, now here let us first show what is x direction, what is y direction, and what is z direction. Wait, from origin this is the x direction, okay, this is the y direction, this is the z direction. I always suggest students to use pencils of different colors because they really help us to differentiate stuff inside diagrams. So it's really important. And in drawing the planes, the axis lines are really important because intercepts are the points where the plane touches the axis line. Okay, so these axis lines are central to drawing planes in a structure. Okay, so since x-intercept is 1, 1 means from origin to the other corner of the unit cell along the axis direction, which is this point. From origin to the other corner of the unit cell, this means 1. Okay, what would half mean? Half mean halfway to this line, which will be right there. Okay, 0 means here, and so on, but intercepts are never 0. We have y-intercept as to be infinity. So how to deal with that? This is one of the point on the plane, as you already know, because x-intercept was 1, so this is one of the point. And let me elaborate, let me highlight it so that we know what are the points on the plane. This is the pink dot. Okay, what next? What we have to do, since y-intercept is infinity, what we do is draw the parallel line. Okay, draw the parallel line from this point, because this is the only point that we know about the plane, parallel to the y-axis. This is the y direction, this is the y direction, and this is the y direction as well. From this point, which is a point on the plane, we'll draw parallel line to y-axis to the other corner of the unit cell. That is how we deal with infinity. Infinity intercept means the points you already know, you have to draw parallel line to the axis whose intercept is infinity. Okay, since y-intercept was infinity, that is why I draw a parallel line. Next is z-intercept is infinity as well. So what we do is, now we know 2 points, this is the point and this is also a point. We'll draw parallel line from each of these points to z direction, and these are the z direction. So we'll draw parallel lines to z direction, not here, from the point which is known to the, which is a point on the plane. From a point on the plane we have to do this. If the intercepts are infinity, if the intercepts would have been different, then we'll have to draw the plane on the axis lines. But if it's infinity, then you have to do that process on the from the points which are already known about the plane. Okay, so that's the difference that you have to keep in mind. Likewise, from this point we'll draw parallel line to z direction, which is to the other corner of the unit cell up to the other corner of the these are the, now join these 2 points together. That is it. This is the, this front, sorry for the line that just got away, this is not included here. This is the plane 1 0 0. Okay, and since it's a simple cubic structure, let us draw the atoms here, because we need to draw the net number of atoms lying on the plane, and this is the plane. Okay, and we know that in simple cubic structure what happens is, this is the drawing for 1 0 0 plane. So let's draw the atoms. We know that where they potentially lie. There is an atom here like that. These are really big atom, and they, you know, like that. At each of the corner of the unit cell we have an atom. Okay, we have an atom at each of the corner of the unit cell, and they are actually touching each other. So we have 4 atoms because we have 4 corners on this plane, and each corner has an atom lying on it. And let each side length be of cube be A. Okay, let's say this length is A. These axis lengths, these lengths which are parallel to axis directions are all A. Since it's a cube, all of the lengths are equal. First of all, let's write the formula for the area of the plane, which is quite simple. This length multiplied by this length, since they are two, it's a square now. That is why in a square the area is equals to a square. That's really simple. And now let's calculate number of atoms lying on the plane. Let number of atoms lying on the plane, let it is equals to capital N. Now let's calculate it, and let me draw another figure for that purpose, because I need to elaborate some steps. I need to elaborate some of the key aspects of this figure. This is the plane, you know, okay, and as I have drawn it, there is a circle here. Plane is a 2D thing, and it includes a 2D part of an atom as well. If you are considering a 3D thing, then you will consider the spherical or 3D equivalent of atom, which is spherical shape of atom. But if you are considering a plane, then you are considering a 2D equivalent thing of a atom, which is a circle, because a sphere has circle as a 2-dimensional cut down. I hope you got it. So we have these circles, and we need to find out the net number of atom lying on the plane. And you can see here, if we consider this atom as a whole, not all of the atom is lying on the plane, only this part of it is lying on the plane. Similarly, for this atom, only this part is lying on the plane, rest of all of the part is outside the plane. Similarly here, and similarly here. These are the only parts. They are not completely into, not the complete atom is inside the plane, but only a part of it is inside the plane. So we need to find out what part of the atom is lying on the plane, and we'll find it out for all of the atoms. Okay, and then we'll add it up to get the net contribution of atom on the plane. So there is a method that I'm gonna show you people that is applicable to all of the planes that we are gonna consider later on as well. So this is a general method, and let's learn it. And if you learn this method, you can do and replicate this method and use this method to find out the contributions of atom to the plane for any kind of plane you're considering, for any kind of structure you're considering. So that's a really simple and general method that you can use everywhere. Okay, so stick with me and learn this method. Once you have learned it, it will become really quick and easy for us to apply. Once you have learned this method, then the application of this method becomes really easy. So let's learn it. Here, let's consider this circle. We know we are doing it in a rough work. Okay, what is the total angle of a circle? Total angle of a circle is 360 degree. We all know about it. Okay, and this is the total angle of a circle, which means the total atom. Okay, now we need to find out this angle between this and this line. Okay, which we know that is 90 degree. We know that. So the angle between these two lines, that are the lines on the plane, angle, let's say angle x is equals to 90 degree. Okay, to find out the contribution of atom inside the plane, what we have to do is to contribution C1, I will say it, is equals to, we'll divide 90 this angle by the total angle. Doing so will give us the part of atom that is inside the plane. Okay, if we divide this angle by the total angle, it will give us the part of the atom that is inside the plane. Not always this angle is 90, it becomes different for different plane. You will see later on when we will do it for 111 plane. Okay, you will see the benefit of using this method. It makes the calculation so easy. So it equals 1 by 4. So this is 1 by 4th contribution by this atom. Okay, similarly, since all of the atoms are same and the shape of them in the plane is also same, so their contribution will remain the same as well. And we have 1 by 4 of this atom, 1 by 4 of this atom, 1 by 4 of this atom, and 1 by 4 of this atom inside this plane. So the net contribution is equals to 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4, and it will become, if you take the LCM, 4 by 4, that is equals to 1. So the net number of atoms that lie on this plane is 1. Now the planar density for 100 plane is equals to net number of atoms divided by the area of the plane, that is equals to 1 over a square. This is the planar density in terms of the lattice parameter A. Now we can convert it into the atomic radius expression as well. For this we need to know the relationship between the lattice parameter and the atomic radius of the atom making up the lattice. This relation could be easily calculated from this figure. This is the center of atom, okay, and this is the radius r. From center to the corner of the atom is radius. That is the thing that we all know, and this is also meant to be a center of the atom. I just haven't drawn the atom in a beautiful way, but the atom center lie on the corner of the unit cell, and this is also the radius of the atom. So we can see that from this corner to this corner we have the lattice, this distance is lattice parameter, which is a. We know that this is the cube length, and this distance is r and this distance is r, so the total distance is r plus r. So a could be expressed as r plus r, so a is equals to 2r. If you want to convert the planar density expression into atomic radius, then we can do it by putting the value of a right here for simple cubic specifically, and it's 2r whole squared, and it is 1 over 4r square in terms of atomic radius and in terms of lattice parameter. This is the planar density in terms of lattice parameter, and this is the atomic density in terms of atomic radius. Okay, so this is the planar density of 100 in terms of lattice parameter, and this is the planar density in terms of atomic radius, and the result that you get comes in a unit of atoms per meter square. Okay, for example, the result you get is 10 multiplied by 12 multiplied by 10 to the power 12. Then you write the units as atoms per meter square. Okay, like that. Atoms per, like this slash that shows division sign, so that division sign per meter square, or you can write it like that as well, as atoms. Okay, you can use the brackets per meter square. Okay, so these are all the ways. Now let's do it for the 110 plane. I hope you got the method, and it will become more clear to you when we'll do it for other planes as well. Let's do it for 110 plane, and link of a video where I'm finding out the planar density for 110 plane and 111 plane for simple cubic unit cell is in description box or in comment section. I actually uploaded a video where I have uploaded all of these parts all in one video. Sometimes students are seeking only for one plane, for example for 100 plane. That is why I separately uploaded them. Still, if you have any confusions, you can ask me in comment section. Goodbye, take care.